Our first speaker tonight is Miguel Montalvo, who is a third-year undergraduate at the University of California, Berkeley.
So first, I just want to acknowledge the NAC program and NRAO, as well as both of my mentors, Loreto and Devaki, for helping me throughout this past summer with the research. I did an analysis of the Luminous Infrared Galaxy ESO 203-IG001, but let's start with some background information on what are these type of galaxies. So luminous infrared galaxies, or LIRGs, are a type of galaxy with large amounts of dust and gas surrounding its nucleus, making it highly obscured. This obscuration, combined with high star formation, make LIRGs very bright in the infrared, due to emission from star formation being absorbed by the surrounding dust and then re-emitted in the infrared and radio. These galaxies are very compact with potential AGN presence, and they are usually at some stage of a gas-rich merger. They can be highly obscured, as I said, so that even mid-infrared observations fail to show what lies inside of the thick layer of dust. And so observations using longer wavelengths like radio are needed to penetrate the obscuring dust and map the physical structure of the circumnuclear ISM. One of the best samples to study mergers is the Great Observatories All-Sky LIRG Survey, or GOLS for short, which is a multi-wavelength study of 202 low ray-shaped luminous infrared galaxies in the local universe at different merging stages. The obscuration we mentioned is clear in this flux limited subsample adapted from Sturwalt et al. 2013, and the 10 galaxies on top of the plot stand out, presenting extremely deep silicate absorption and weak PAH emission, suggesting that the bulk of the obscuration, as well as the infrared luminosity, arises very close to the buried nucleus, within about 1 kiloparsec, which is expected for late-stage mergers. These are then two other distinct populations in the plot that are well classified as powerful starbursts on the lower right, and then naked QSOs on the lower left. In a model presented in Hopkins 2008, the star formation rate is plotted as a function of the phases of growth in a typical galaxy undergoing a gas-rich major merger. And the model described how SFR stays constant, and then until they experience close interaction, the SFR gets enhanced in late-stage mergers. This subsample of highly obscure galaxies may represent a brief transition between in the evolution of a gas-rich merger to an optically visible QSO. So I wanted to analyze ESO 203-IG001 because this is one of the most obscure galaxies in the plot that I showed, and that it's visible to ALMA. And so we have already some information about this galaxy. We know that, we have here an optical image from the Hubble Space Telescope. And we know that this galaxy has a luminosity of 10 to the 11.86 solar luminosities from Armus et al. 2009. And it is at a distance of 234 megaparsecs with a redshift of 0.05 to 9. And the star formation rate of the source was derived from the infrared luminosity, obtaining a value of 88 solar masses per year. And this is normal for LIRGs and LIRGs. And it is also very high compared to spiral galaxies like our Milky Way, with a star formation rate of about 3 to 4 solar masses per year. We also calculated the molecular gas from the CO intensity in Mirabel 1990, obtaining a value of 5.2 times 10 to the 9 solar masses. And then in the next image, we can see the observation setup. The CO is commonly used to trace the total molecular gas within a galaxy. However, HCN and HCO plus, they have higher critical densities. And so they trace the dense gas that is actively associated with ongoing star formation. So I use data from ALMA band 7 using 4 spectral windows targeting HCN, HCO plus, CS, and the continuum emission at about 870 microns. This was data from the archive with a time on source of 11 minutes. As you can see here from the atmospheric transmission curve for ALMA, for spectral windows 29, which was intended for the continuum emission, and spectral window 31, which was intended for CS, the atmospheric transmission is poor. The lower the curve is here, the poorer, the more poor that is going to be the observations, and therefore spectral windows are noisier. And because of this, I decided not to include these two spectral windows for the continuum imaging and only work with spectral windows 25 and 27, which were targeting HCN and HCO plus. And then the continuum, I got it from the line-free channels in these two spectral windows. So for my results, here I present the integrated emission, the continuum emission, and we detect this continuum emission, sorry, whoops, okay, there we go. We detect this continuum emission with a total flux of 10.6 millijanskis at 337.7 gigahertz. We also perform a 2D Gaussian fit into this image so that we can obtain the sizes. And then from the sizes, we can say that this source is marginally resolved. We can also see the contours laid over on here, which are multiples of the RMS noise. Then the dust mass was calculated from the integrated flux, resulting in 8.9 times 10 to the 7 solar masses. And we can then go ahead and do an order of magnitude estimate, as Wilson did in 2008, which is going to be about 100 times the dust mass. That is going to be the molecular gas mass. And so about 9 times 10 to the 9 solar masses. This value is within the same order of magnitude as the one that we calculated from the luminosity. Then for the line emissions, we have here the integrated emission for HCN and HCO plus with contours laid on top that are fractions of the peak flux. From the images, we can see that HCO plus is a little bit more extended. And so we did this moment zero map, which is the integrated emission, to get both HCN and HCO plus. The integrated flux was calculated in two ways. The first one using a 1 arcsecond diameter circular aperture centered on the emission, and then from that aperture, we extracted the spectral profile from the region to later do a fit of the line and integrate the flux over the line panels. The second approach was to perform a 2D Gaussian fit on the moment zero map and then get the integrated flux. These two images that you can see on the back are the residuals from this 2D Gaussian fit. And so if we take a look at the spectral profile, we can see that HCN is brighter. There is some enhancement. And we can also see that as we saw from the moment zero maps, HCO plus is a little bit more extended. And we can also see that from the sizes here. In this table, I just present all the results and data that I obtained from these two methods with the rest frequencies of HCN and HCO plus here as well. The most interesting parts were from the moment 1 and moment 2 maps, which are the intensity weighted mean velocity and the intensity weighted velocity dispersion. So here we can see a gradient in color, which represents the red shifted and blue shifted velocities for this molecule. And along this axis of the gradient, that is where the major axis of rotation is going to be for these molecules. So what is interesting is that for HCN, we have the major axis of rotation with some angle with a PA of 53.2. But then for HCO plus, it's not aligned in the same direction. This one is pretty much horizontal. And that is not something that we would expect. We would actually expect that they're both in the same direction of the axis of rotation. And then we also notice that from the intensity weighted velocity dispersion, for a rotating disk, we would expect that the velocity dispersion would peak in the center. And we do see some higher velocities towards the center, but then the peak velocity dispersion is actually off-center, both for HCN and for HCO plus. And then on top of this, if we can also go back to the Hubble Space Telescope, the optical image, we can see, you might be able to see these two obscure conical regions that are coming from the center of the galaxy. And these two obscure conical regions happen to be aligned with the direction of the velocity dispersion. For HCO plus is pretty much vertical, which aligns with this one here. And then HCN, it's at an angle that aligns with this other obscure conical region. So this might be indicative of an outflow, but we cannot say that for sure because we need to do further analysis. But it's something very interesting and something that we didn't expect. And so as a future work, that's what we will want to do, a kinematic analysis, maybe using GALPAC, to get more information into these weird rotating disk observations that we have. And then also another thing that is important is that this is a very faint source, and we only had 11 minutes of on-source observation. And so we would try to go for deeper observations, and ideally we would also want higher angular resolution, even though this might not be possible or feasible because of how the cost that it would have in time. But then we can try at least deeper observations for this source so that we can have a higher signal and then perform this kinematic analysis to see what is going on with this galaxy. So this is the research that I worked with over the summer. And thank you. Any questions?
I am fascinated by the fact that in the velocity maps, the kinematic major axes of the HCN and HCO plus are different from each other. Do you know anything about whether this galaxy might have an AGN at the center? Because I think that can sometimes cause differences in distribution for HCN and HCO plus.
Yeah, we don't have data on that. That's something that we would try to confirm. And then also something that might be also like if there is an AGN in this galaxy, then that would also maybe not explain, but that would also align with the fact that there is HCN enhancement over HCO plus. That is something expected for an AGN within the galaxy. So yeah, that would be something that we would need to confirm with further analysis.
Great, thank you.
Have you considered other tracers to look at besides HCN?
Yeah, that is something that we were also talking with Loreto and Devaki, maybe trying different tracers to see if we can also see different like rotations. Actually, for this data that we had, CS was also intended, but the fact that the source is very faint, we were not able to use that data for CS, but maybe that's why the fact of maybe doing deeper observations so that we can have a higher signal, we could also probe for CS and maybe other tracers to see if that also has can gives us more insight into this weird thing.
Would CO be another tracer that maybe you would be able to look at, being that that's also a good star formation tracer?
Could be, yeah. We haven't talked about which specific tracers we could aim for, but yeah, that could be also an option.
Got you. Thank you. Great talk. I really enjoyed it.
Thank you.